When we learn the power series notations, Taylor and Maclaurin series are two main definitions that are being used. And the meaning of these two definitions are when you express any function as a power series within a certain radius of convergence, there's another name called the Taylor series. Now, for example, we say that this is the Taylor series of Ex at 2. That is the Taylor series of Ex at 2. So, and also instead of this at 2 part, you can say that this is the Taylor series of Ex about 2. Also, you can say it as the center of 2, right? So, you can call this as the Taylor series of Ex centered at 2. So, all these names can be used. Now, the main point I wanted to highlight is this name Taylor series, right? And for example, this one is the Taylor series of sin x at 0, and this is the Taylor series of, we didn't write down a specific sigma notation, but you can generally say that this is the Taylor series of sin x centered at pi over 3, and this is the Taylor series of cosine x centered at 0, and this is the Taylor series of x cos x centered at 0. Likewise, you can use this name Taylor series. And if the center is 0, there is a specific name called the Maclaurin series. So, if you have a center at 0, now this is not 0, right? But here you have a center at 0. So, you can either call this as the Taylor series of sin x centered at 0, or else you can call this as the Maclaurin series of sin x, because when you say Maclaurin series, you don't have to mention the center, because within that name itself the center is hidden, right? Like center is obvious when you say the Maclaurin series. So only when you have a center 0, you call it as the Maclaurin series, or in general you can call this as the Taylor series centered at 0, right? Now let's have a look at the Taylor series of this function centered at 2. Let's see what will happen when we are going to calculate the Taylor series. So the Taylor series means this one, and we had the result that we obtained in the previous calculations, which is this one. So by using this, let's see what will happen when we calculate the Cn coefficients. Now here C0 is equal to the 0th derivative. That is, as I explained before, the 0th derivative means the normal function, just the general function, right? So here it is this one. So 0th derivative evaluated at 2 means the normal function, the initial function evaluated at 2, and 0 factorial is equal to 1. So the C0 is equal to 12, and for C1, that is the next term, because now you can, if you expand this one, it will be like C0 C1 x minus 2 to the power 1, C2 x minus 2 to the power 2. Likewise, it continues, right? So this is almost the same thing as I explained in the previous video set, right? Now you can see that the first, C1 coefficient is equal to 6 and C2 coefficient is equal to 1. But after that, what happens is, you can see that the second derivative is equal to 2, that is a constant. So after that, all the other derivatives will be equal to 0, right? Because when you differentiate this one, you will get 0, and when you differentiate 0, you will still continue to get 0. So from 3 onwards, from the third derivative onwards, you will get 0 as the answer. And that means Cn from n equals 3 upwards, you will get 0. That means in this expansion, from here onwards, this is 3x minus 2, 3xc4, x minus 2 to the power 4. Likewise, you have the expansion, but from here onwards, all these coefficients will be equal to 0. So what remains is only these 3 terms, right? So in our Taylor series expansion, we have a finite number of terms, right? So if we write down the expansion of this given original function, then it will be like this, right? So in fact, that means x to the power 2 plus 2x plus 4 is equal to 12 plus this one plus this term, right? Now keep this relationship aside and just try to solve this one separately. So what will happen if we try to do that? This is 12 and this is 6x, and this will be minus 12x, minus 12 plus x squared, and if we expand this one, it will be minus 4x plus 4, right? And this will be equal to x squared will be there, and 4x and 6x will give you 2x, and this 12 and this negative 12 will get cancels out, leaving out with 4. See, this is the same as this one. So sometimes you might get the question like, why is it necessary to do all these calculations? Because it's kind of obvious when you do the expansion, right? It's kind of this very same, the identical terms are written, although this looks like a different function. It's identically the same as it was in the left hand side, but only difference is that the way they have expressed it. Other than that, these two are kind of identical. So what's the use of doing all these calculations if we can write this down directly? So the answer is kind of funny, right? Now it's true that these two representations are equal. In fact, that is the main reason for having an equal sign in between, right? Because equal sign itself say that the two quantities on the left and the right hand side are equal, right? That's the basic idea of the equal sign, right? But the problem, the interesting part here is, although this equality is kind of obvious to us, it will not be obvious when you have things like this, right? So if you write a trigonometric function as a series representation, it's not obvious at all, right? Here you have a trigonometric function, here you have a addition of polynomials, which is like totally weird situation, right? So but the thing is, now writing this equation was obvious, right? But now here, although it was obvious, we still had this equal mark, right? So this equal marks carries a certain strength, right? So it's like you say that the quantity in the left hand side is the same as the quantity in the right hand side. So that same strength, that same special property is still there for this one as well, right? Although it is not obvious, the same strength, the same property exhibited by this equal sign in this very obvious result is still there in this equation also, right? So it's a very nice application of relating two quantities which seems to be totally different, right? So this is the importance of having a power series notation, and this importance will be highlighted more in the next video when we are drawing some curves of these two functions on the two sides. So the main point that you have to gain from this video is that the same strength that this equal sign had was still there in this relationship also, but this relationship is not that obvious as it was in here.